Hello, welcome to this video of the classics. Today I'll be talking about this differential system. So let's take a close look at it. So we've got three unknowns that are an unknown that depends of t and that are linearly dependent from each other, and there is also a term um, exponential t here and minus t exponential t here. So this is kind of complicated. So at first we'll solve the homogeneous version of this. So without this thingy here and without this thingy here. So we can write it with a matrix writing. So I'll call A this matrix that is actually just like placing the numbers in the matrix here. So I call key, it's a Greek letter, the polynomial associated with the matrix. So by definition, it's the determinant of x times the identity minus the matrix. So this will help us getting the eigenvalues, so the spectre, spectre. So we do that operation, and then we notice that um, there is a -1 here and -1 here. So what I will do is the column 2 will be I will add column 2 with column 1, and I will store that in column 2. So I do that operation. -1 plus 1 equals 0. X minus 4 plus 2 equals x minus 2, and 1 plus x minus 3 equals x minus 2. So to do this operation, you actually have to like sort and know how to do this. Sometimes you will not see that there is a -1 and a 1, and then that you get x over x minus 2. Um, but it's like before doing the hard strats that are like the Sarris method and Sarris formula. You can actually try to see if there are things like that when you add two lines or two columns, and that you get some kind of interesting results. It's faster, but like you won't see it most of the time. So I guess uh, x minus 2 I factorize by this, and so I get 1 and 1 here and a 0 here. So actually I took that problem from a book that I haven't solved myself. So I don't know if you can factorize it more. So I just let it like this and used development by the first line. So I've got x minus 2 times this bracket. So x minus 5. So I do the first thingy. The x minus 5 is times the determinant of this matrix here. So this one here, plus 0 times another matrix, another determinant, plus 1 times this determinant here, that is here. So we continue the calculus. Here this determinant equals to x1 times x minus 3, so x minus 3, minus 2, so x minus 3 minus 2 equals x minus 5. So, and this part is equals to minus 2 minus minus 1, so minus 2 plus 1, that is equal to minus 1. So we get x minus 1 squared minus 1, and that is actually equal to x minus 2 times x minus 5 minus 1 times x minus 5 plus 1. So we get x minus 2, x minus 4, x minus 6. So actually I want to say something. Most of the books you'll encounter will say this implies that the spectre is this. Yes, but also no. Actually, there could be other values. You have to say that the dimension of A is equal to 3, because there exist other matrices where the eigenvalues will not appear, or will have a multiplicity order that is non-trivial. So here we say that the dimension of A is equal to 3. So it means that at since I have already 3, their multiplicity must be 1. And since 1 plus 1 plus 1, so 1 here plus 1 here plus 1 here, equals to 3. So I can't have other thing. So it's important to have that step. I know that in English university, also English in America and Australia, this step isn't required, but it's actually really important. So we know that there are no other eigenvalues. So the spectral complex of A equals to 2, 4, and 6. So we'll calculate the eigenspaces. That is by definition the care of A minus 2 identity. I won't solve this, but I plan on doing a video about how to do a diagonalization. So we get this. Oh yeah, also what I call vect is actually the French SP operator, so span in English, I think. And this SP corresponds to the spectre, so the list of eigenvalues. So we do the same thing with 4 and with 6. This one is actually 6. So I call D the diagonal matrix of 2, 4, and 6, and P. So I set the eigen vectors here, and we get this matrix. So we can write that A is equal to P D P minus 1. So I call X the matrix with x1, x2, x3, and I call Y a matrix of y1, y2, y3 that are actually the same, but with the matrix P that change the base. So we know that y squared is equal to dy. So we get that result by just calculating. Oops. So we get that result by calculating. It's just like the eigenvalues. But now we integrate because we can. And since we're just interested by the homogeneous, because since here we just find the x0, so the homogeneous. There is no plus c here in the integration. It's this. So we have our generating solution y1, y2, and y3. But since x is equal to py, so we can just write it like this. So we know that x is equal to y is equal to this one plus this one, since from this one you see you have 1 and 1, so you'll do 1 and 1 and so on. So since there is a 1 here and 1 here, you'll have this one plus this one. Since for this one there is 1 here, 1 here, you'll have this one plus this one. And then since here is these two ones, you will have this one plus this one for x3. So now we have our general solution without this thing here. So also I didn't mention, but where is it? A are just complex values that depends on the problem, but that are not specified. So it's part of the complex space. So now we find the particular solution of our system. So I will call U1 and U2 um, some spectrum, so that B on T is equal to the system. So y squared equals to um, equals to no x squared of t is equal to, wait, I'm going to write it because let's set b so that y x squared x squared x prime equals to x, well, so ax, it's not actually ax, but it's this system, so I'll call it s that depends of x, plus b. So we have our general solution that is actually the system here that we solved. So we have on the first coordinate a2 x and so on, plus b over t. So well, no, actually I'm saying shit. Yeah, it's x. Okay, so I transform this. Where is it? I transform this, so we have x squared, so x1, x2, 3, x squared, wait, keep saying x squared, x prime is equal to x1 prime, x2 prime, x3 prime, that is equal to some linear span of this, plus another part that is actually this and this. So b of t is equal to t et of u1. u1 is equal to 0, 0, minus 1. The minus 1 comes from the part that the minus is here for t et, and the 1 here comes from the fact that we have the exponential t here. So the general solution is here. That's what we say just by using the column. Okay, I miss a step here. So I call C1 and C2, so that, so okay, so I know that the generating solution is span of two orthogonal subspaces, and I know that t exponential t is orthogonal to exponential t, so there it's legit to write this, to say that the particular solution is equal to this for some value c1 and c2 that we'll try to determine. So we get that x0 squared prime is equal to this, that just factorizing, because yeah, because we have from the system. So yeah, so we continue. We have this part here that is equals to this part here from the matrix. So we have this one for B and this part for the general solution. So we get this by identification, because we have something times t exponential t that we have here, so we get this, and something times exponential t that is here. So by calling the matrix F that is equal to identity minus A at the inverse, we notice that C1 is equal to FU1. So you have this, And for C2 you have F times C minus C1 plus U2. For this it's actually like kind of cheating, because it's like you have to notice it, but there exist other ways of solving it. So the computer gives us for F, that is the inverse of identity minus A, gives us this result. So C1 is actually the first yeah, is actually this one uh, minus this one, because C1 is FU1. So you do 0, 0, minus 1 times this matrix, that is equal to this. And for this one, you do U2 because of this, because F equals to minus C1 plus U2. So you do that and you get this result. Okay, so this part is actually really tricky. Usually they will ask you the like only this part, but this is actually really kind of hard. So yeah, it's complicated. So we get the solution that there exists A1, A2, A3 in the complex plane, so that we get all of these results. And that's it. So yeah, I think you liked. I hope you liked this video. If you have any question, feel free to ask, and I'll be glad to answer them. And thanks for watching, and bye.